Hi to all. So today we are going to see a new topic, partition coefficient. So in physical science, a partition coefficient or a distribution coefficient is the ratio of concentration of a compound in a mixture of two immiscible solvents at equilibrium. Okay, I think you get the point. So we have to see the concentration. So that has to be in two immiscible solvents. So it may be the solute of a drug. This ratio have comparison of a solubility of the solute in these two liquids. The partition coefficient generally refer to the concentration ratio of an ionized species of a compound, whereas the distribution coefficient refer to the concentration ratio of all species of the compound. That means ionized plus unionized form. Okay, so here we have a definition for the partition coefficient, the ratio of concentration of a solute in a two immiscible or slightly miscible liquids or in two solids when it is in equilibrium across the interface between them. Okay, so if you see, most commonly one of the solvent is water, while the second is obviously hydrophobic, such as 1-octanol. The partition coefficient measures how hydrophilic and hydrophobic a chemical substance is. A partition coefficient are useful in estimating the distribution of the drugs within the body itself. Hydrophobic drugs with high octanol water partition coefficient are mainly distributed to hydrophobic areas such as a lipid bilayer of cells. Okay, so this is the overall explanation of the partition coefficient. So here we have the calculation part of the partition coefficient. So if you see here, so let's draw the formula here. So if you see the partition coefficient, that denoted by P equals to a drug in octanol, so followed by the drug in water, otherwise aqueous solution. Okay, so typically over a small range of log P, for example, if you have the log P, so in the range of 1 to 4, the log P in the range of 1 to 4, so we are going to estimate a straight line, so that is obtained. So straight line is obtained if you see the value for log the inverse of concentration, that equals to 0.75. okay, log P, so log P 2.30. so this is for the straight line. So if the graph is extended, to very high log P values, then get a parabolic. So we are going to see the parabolic curve there. So apart from the straight line, we are going to see the parabolic curve. Here we are going to get log inverse of concentration 2 minus K1. So we'll see minus log P, what it indicates, square, plus K2. So K2 we have log P plus K3 here. So we'll see when partition P value is small, so that dominated by the log P term. So when P small, it's obviously dominated by the log P term. When P large, log P squares dominates, and so activity is going to be decreased. Okay, so if you see the overall equation, so logarithmic equation, if you see the partition abbreviation P is defined by its concentration on both the faces. Okay, if you see in the ratio as a log P there, so we can give as a log P octanol by water, that equals to log, so we are going to see a solute, that means a drug, so which is in a unionized ionized in octanol and ionized in octanol, then followed by the solute, that means your drug, in unionized water form, in unionized in water form. So let's imagine this is the overall equation. To a first approximation, the non-polar phase in such experiment is usually dominated by the unionized form of the solute. So we have the previous graphs, so you can denote this line, which is electrically neutral. Through this may not be true for the aqueous phase. Okay, to measure the partition coefficient of unionizable solutes, the pH of the aqueous phase is adjusted such that a predominant form of the compound is, so predominant compound in solution, in that solution is in unionized form. Okay. So otherwise it is going to measure at another pH of interest requires consideration of all species, unionized and ionized form. Okay, so this entire scenario, corresponding partition coefficient for unionizable compounds. So unionizable compounds, if we are going to give the representation as unionizable compound, log P is derived for cases where there are dominated ionized forms of the molecule, such that one must consider the partition of all forms, ionized and unionized forms. Okay. So then here, so if you see the overall equation for this, so how we are going to give as a log P I octanol by water equals to, open the brackets, with log solute I am in octanol, solute ionized in water. Okay, this is the entire algorithmic of corresponding partition log Pi octanol by water is defined in the same manner as for the unionized form also. Imagine it is an ionized, we have the unionized in similar manner. Okay, so then what are the factors that's going to affect your partition coefficient? What are those things? So what are the factors it's going to affect? See here. So we have the factors like pH, cosolvent, surfactant and complexation. Partition coefficient are difficult to measure in living species. They are usually determined in vitro. 1 octanol as a liquid phase and phosphate buffer of pH 7.4 as the aqueous phase. This is the thing you have to be very careful. 1 octanol as a liquid phase, because, so what may be the reason to choose the octanol? So 1 octanol has been chosen because of it has a polar and non-polar region. Then partition oil by water is easy to measure, then followed by often correlates with many biological properties, followed by predicted using computational model. Okay, so these are the criteria. The partition coefficient P is dimensionless and its logarithmic log P is widely used as a measure of lipophilicity. Okay, the log P is measured by the following methods: shake flask followed by chromatographic method. So we'll see how it's going to measure by the shake flask here. So let's draw the shake flask method. So before that, we have the word that phenobarbital has a high lipid water partition coefficient of almost 5.9. So these are about phenobarbital. So phenobarbital, yes, these are about the partition 5.9. So what? So it will have almost high lipid and water partition. Then apart from that, thiopentone sodium has a chloroform water coefficient of about 100. So it is highly soluble in lipid. Hence thiopentane sodium is used as a ultra short acting barbiturates you have to keep in mind. So due to its reason, we have to frame this drug in a classification such that it has to come under ultra short acting drugs. Okay, it is an ultra short acting drugs. Okay, otherwise it's barbiturates, no, ultra short acting barbiturates. So here, apart from that, so if you see how the shape flask method is carrying on, so shape flask method is carrying based on the experimental part. So by taking a separating funnel here to this separating funnel, so we have the lid on one side and we have so imagine we have the lid here. So here I am going to draw a two partitions. So here we have an octanol, then followed by aqueous phase. Okay, so if you are going to add a solute here, then you have to go for shaking the flask. So while shaking, the solute is going to distribute in between the two. So it's going to distribute between these two phases. Okay, so after this you have to go and estimate. So after this you have to go and estimate how much you have been attained. That means how much concentration of the drug that has been penetrated. Okay, so yeah, we have the word on partition coefficient. So we are going to explain the experimental part. So how the shake flask method is going to carry on. So here the shake flask method, we have the separating funnel. So we are going to add the solute. So solution that is in a two form, solution of the drugs in water, solution of the drug in one octanol. Shake and allow the phase to separate. Then after that you are going to see the two layers. One is octanol phase which is having a turbidity, then aqueous phase, so maybe it's in colorless, so it's in light solution. Then you are going to extract these two solutions in two separate containers or beakers. Okay, so the two solutions are mixed vigorously by shaking. So after that the concentration of the compound in each layer determined by suitable analytical method, then resulting concentration into directly, so given, otherwise substituted in the equation. So give the p and finally we are going to convert into the log p value. Okay, so this is the overall estimation of the partition coefficient by shake flask method. So if you see each and every drug we have so particular partition, that means a log p value. So we have a log p value, for example oxytetracycline. So for example oxytetracycline, we have the negative value of minus 1.12. sulfadiazine, so we have the value, that's a positive indication 0.12. So similarly for aspirin, we have almost 1.19. Okay, for benzopenicillin 1.83, lidocaine 2.26. so these are the values. So what it indicates, what the values indicates here, negative log p, what it determines, negative log p value are compounds with greater solubility in water than non-polar organic phase. These are indication for the negative. Compounds polar, that are well solvated in aqueous medium but diffuses poorly into liquid rich media. The compounds have poor absorption from the gastrointestinal tract. Compounds with log p value between 0 to 0.1 also poorly absorbed into the lipophilic media. Okay, this is the entire so history about partition coefficient. So then apart from that, it is the ratio sum of the concentration of the compound in each two phases. So what we are going to see now, that's a distribution coefficient. What is the need to discuss the distribution coefficient? Is the ratio of sum of the concentration of all forms of the compound. That means ionized plus unionized in each of the two phases. One essentially always aqueous, as such it depends on the pH at the aqueous phase. Therefore, log D distribution equals to log P partition for non-ionizable compounds at any pH. At any pH. Okay. For measurement of distribution coefficient, the pH of the aqueous phase is buffered. You have to go for buffering the solution to have a specific value such that the pH is not significant. Then we are going for the introduction of the compound. The value of each log D is determined as a logarithmic ratio as follows: log D, so denoted by octanol by water, equals to log, so log solute the mean drug solute. Here we have to go for ionized octanol by solute. Here solute, then we have to go for ionized in water. So then followed by the solute unionized in octanol, similarly unionized solute. Sorry for the inconvenience, I have to write very clearly, I don't have much space here, I will try now. Okay, so this is the overall equation for the log D. Okay, distribution coefficient of log D. So here the above formula what it indicates now, so ionized each indicate the sum of concentration of ionized species in their respective phases. In addition, since log D is a pH dependent, the pH at which the log D was measured must be specified in areas such as drug discovery areas involving partition phenomena in biological systems. So this is mandatory, such as human bodies. The log D at the physiological pH 7.4 is a particular interest there. So this is about the partition coefficient. If you see the importance, so what is the need to see the partition coefficient? So here partition coefficient importance, it is generally used in combination with the pKa to predict the distribution of the drugs in biological system. The factors such as absorption, excretion and penetration of CNS may be related to the log P value of the drug. The drug should be designed so with the lowest possible, so we have to make it a lowest possible terms, log P to reduce toxicity, non-specific binding and bioavailability. Okay, so these are about the importance of partition coefficient. Then apart from that, so we have hydrogen bonding. So we know that hydrogen bonding, if any hydrogen is making a covalent bond with a nearby atom, so it must be, apart from the carbon, it must be a negative atom, electronegativity atom. The hydrogen bond is a special bond, dipole-dipole interaction between hydrogen atom in a polar bond such as NH, OH and FH. That means nitrogen, oxygen, then followed by the fluorine. So these are nothing but the electronegativity. Dipole results from unequal sharing of electrons between the atoms within a covalent bond. These are weak bonds denoted as dotted lines, we are going to see here. So these are weak bonds, they are going to denoted by the dotted lines. So here if you see these bonds, the hydrogen is going to make a dotted bond with another atom. Okay, with another atom. So the compounds that are capable of forming hydrogen bond is only soluble in water. So based on this we have the two feasibilities, intermolecular and intramolecular bondings, intermolecular then intramolecular. So what it will show, so see here intermolecular, it is the reason of occurring between two or more than two molecules of the same or different compounds between the atoms. Due to this increase the boiling point of the compounds, further molecular weight of the compounds requires more energy to dissociate the molecular vaporizations. See here I have the water molecule I am going to draw, so which has a dotted bond with a nearby hydrogen atom. So then if you see the amine bond, so with water, so it's going to make a weak bond with nitrogen, is going to make a weak bond with, so otherwise we will draw here, nitrogen is going to make a weak bond with hydrogen. So these are about the amines. Then let's see the bond with, sorry I have the dotted lines, I have to draw the dotted lines. Nitrogen, so nitrogen making a dotted bond with a nearby hydrogen of the amine. Okay, so if you see the bond with water and amine, so the oxygen is going to form a dotted bond with a nitrogen. Okay, so this is an so transition matching. Now what about the intramolecular hydrogen bond? Hydrogen bonding occurs within the two atoms of the same molecule. This type of the bonding is known as chelation and frequently occurs in organic compounds. Sometimes hydrogen bond develops 6, otherwise 5 membered rings. 6 otherwise 5 membered rings. Due to this nature, it's going to get an so decrease in a boiling point. If you see the intermolecular bond of salicylic acid, we know that groups are going to present on ortho position. So where your hydrogen is going to make a bond with the oxygen. So similarly, if you are going to take the nitrophenol, so this nitrophenol so is going to make a bond with the hydrogen oxygen atom, then oxygen atom is going to make a bond with the oxygen atom of nitrophenol. So this is about the intramolecular hydrogen bonding. Salicylic obviously have an antibacterial activity. Okay, so if you see the para and meta hydroxy benzoic acids, para and meta hydroxy benzoic acids, so both will have, so para and meta hydroxy benzoic acid both will have almost inactive. Okay, then see the factors that's going to affect the hydrogen bonding boiling melting point. So these are all the physical properties affected by hydrogen bonding, boiling, melting, water solubility, strength of the oxide, so strength of the acid, then followed by spectroscopic properties, surface tension, viscosity, biological products, drug receptor interactions. Okay, so we have a series of properties we have been extracted. So some of these properties, so that's going to affect by the hydrogen bondings. Okay, so we'll see in next class.